Next paper is on contributions from microbies and control, calorimetry studies of the interaction of oxygen with slow complexes on MgO. The paper will be given by Professor Saul.
Thank you. Well, here then is the title of this paper. It's concerned with the CO complexes which form on highly outgassed magnesium oxide, and the paper is concerned with calorimetric studies on the interaction of oxygen with those complexes. Now, the discovery of these complexes which form on highly outgassed MgO is a fairly old one now, and the feature which I want just to remind you about in the first few slides is the fact that a spectrum develops in the ultraviolet and visible and is characterized as you increase the exposure of the solid to carbon monoxide. It's characterized by these two strong bands which develop. This band, notice, and this is the unit of reciprocal centimeters, 20,000 reciprocal centimeters, or 500 millimeters. There are some merits in using an energy scale rather than a wavelength scale because, of course, the shape of the bands makes more sense, strictly speaking, when you are using an energy scale. Now, the more recent studies have been concerned with the build-up in the initial stage, and on the slide, may I have the first slide please, you see the same feature about this time. This is the same type of representation. Here though, there is a wavelength scale, and you see that these two bands do develop ultimately, but there are some other features which occur at the very early stages of exposure. Now, what I would like, however, to point out is that these strong bands here relates to the formation of complexes which are multinuclear. And they are species which are akin to cyclic complexes of this kind, where the CO molecules have collected together in a cluster, and you have a kind of rhodizonate complex here, which has aromatic stability and color, because these species, as we can see from the slide you've already put on, as you can see from the color here, it's a red color. Now, if you study the build-up of these species calorimetrically, what you find is that the heat of absorption of carbon monoxide is of the order of 60 to 80 kilojoules in this initial region, and then it settles down to a value which is of the order of 50 kilojoules per mole of CO. Now the complex here, this one, is building up only slowly in this region of pressure. It does not occur initially. In the initial stages of pressure, all that one is seeing are these small regions here in the build-up of this band. Now what is happening is summarized on the next slide, and I don't wish to go into the details here, but I want just to focus your attention on three things. Could you focus it first, though, in order that we can see it? Thank you. Just notice this species, which is the initial formation of carbonite, CO2 2-. Then there is the build-up of linear species which have ketenic structure. And then finally, there is the development of the cyclic species. And infrared spectroscopy Incidentally, it is a very complex infrared spectrum, but infrared spectroscopy shows that there is some carbonate formation in these final stages. So that three features there: carbonite at the beginning, ketenic, and then cyclic species together with carbonate. Now, after that preamble, let's move to the oxygen effect. So we pre-sorb this carbon monoxide, we evacuate any unreacted CO, and then we dose oxygen and measure the heat of absorption. Now what we see here is an enormous heat. Remember on that previous slide for the heat of absorption CO, it was about 60 kilojoules per mole. Here oxygen, 600 kilojoules per mole. High reactivity, very exothermic process. And here are the first 5 doses. Ultimately, however, something begins to change in this region, and finally the heat drops dramatically as you, as it were, complete the titration with oxygen. The coverage which we had at the beginning, and which you may have noticed on the previous carbon monoxide heat curve, the coverage expressed as CO molecules per ion pair was around about 0.02. The coverage which we find when we do this oxygen titration in terms of oxygen atoms is around about 0.01, so that there is about 50% of the oxygen taken up which would oxidize the whole of the CO2. Now there is a second thing which can be done with regard to these calorimetric experiments. We can measure the rate at which the heat is evolved when the doses are admitted. And extra information comes when you do that, and it is simply represented if we take the time to reach the peak in the heat release. Now, these experiments are done in a heat flow calorimeter, a Calvé microcalorimeter, but there is a maximum in the heat flow after a certain number of tens of seconds. It can be minutes, it can even be hours in some cases. The calorimeter is quite capable of coping with that. But let us see the way in which the time to the maximum varies across those increments which we have already mentioned. Here now we see the way in which the time to the maximum changes. And after a first few doses, we see that there is a considerable slowing down in the rate of reaction. There is still a very high heat evolution here, but the reaction has considerably slowed. Moreover, there is carbon monoxide displaced into the gas phase. Now, when I showed you these data for the heat of absorption, I have already corrected for the amount of carbon monoxide which has been desorbed. Let me just push the top curve up now, because you know that it is a plot of tau, and here are the same data that we have seen before. And what I want to stress is that the value of the heat in these cases has been corrected for the heat of desorption of CO which has occurred in this region. But both sets of data now have comparable information to divide the process into 3 stages. We can see that there is a first stage where there is very little displacement of CO. there is an almost total reaction of the complexes with oxygen. Then we come to a second stage where there is more evolution of CO and there is a slowed reaction, stage 2. Stage 3 represents the tail end of the titration. Now the process has become again rapid, but there is a negligible amount of oxidation. 3 stages there. Now what does this all mean? Well, we have the possibility to look at the reaction in terms of the uptake. Now when we do that, in the experiment I've described, we started with a coverage which was equivalent to that which would be 0.023 if the CO had remained intact as CO molecules. We have seen that the limit of uptake of adsorbed oxygen when expressed as oxygen atoms is 0.012, so that is 54% of the theoretical value for total oxidation to CO2. And as we already heard from Kalucha, it of course forms CO32- on magnesium oxide. So that's the situation as regards uptake. Only about 50% of the CO which is on the surface can be oxidized. We are carrying out these experiments at a temperature of 303 Kelvin, 30 degrees centigrade. Now what about the heat evolution? Well, the theoretical value, if there is total oxidation to the carbonate, has to take into account the heat of formation of the carbonate from CO2. We know this value, of course, from the thermodynamic tables. This value, 117 kilojoules, is the heat of formation of magnesium carbonate. I will show you in a moment that the heat of absorption of CO2 on MgO is very close to this value. But the total heat measured for reaction 1, this reaction, was 47% of the heat calculated for reaction 2. So that there again, we have about half of the heat evolution that we would expect. Those are the data, by the way, for the adsorption of CO2. You can see that the value in the heat of adsorption experiment is very close to the molar heat of reaction of 3-dimensional magnesium carbonate. So what are the implications? The implications are that there is either a kind of general partial oxidation of the complexes, or there is a near total oxidation of a fraction of the CO species, or there is a mixture of A and B. Now we can calculate the heat that we would expect if there was total oxidation if we take into account the heat of absorption of carbon monoxide. As you know, we measured that. I showed you the heat of absorption data. The heat of absorption of CO is of the order of 50 kilojoules per mole. So the heat to be expected if the oxygen oxidizes the adsorbed CO-derived species completely can be calculated if we make use of that value. Here is the absorption of CO to CO adds, and here is the oxidation to carbonate. It works out to be 350 kilojoules per mole of CO, or of course, if you express it as per mole of oxygen, it will be twice that value. Now, do you recall the figure which we had? It was of the order of 600 kilojoules per mole of oxygen, so that we are a little less than the theoretical for total oxidation, but not much less in the first few increments. The uptake and the evolved heat then are less than the theoretical for total oxidation, but the molar heat for the oxygen which does react in that first stage approaches the heat of total oxidation. So the picture is that the complexes form on the surface. There are more than one kind. We saw two big absorption bands. About half of that material is reactive towards oxygen and about half is not. What does the spectroscopy show? Well, if we now return to ultraviolet visible diffuse reflectance experiments, here are the two bands which we saw at the beginning of the talk. There is only a small change here when one evacuates the carbon monoxide. This gives you spectrum C. So this is the starting condition when we dose the oxygen. Notice that dosing oxygen for just a very brief time of 2 minutes completely kills this band and reduces to a rather lesser extent the band here. So that the species which are being titrated with the calorimetric experiment are primarily these cyclic species giving rise to the aromatic character, the cyclic species, which are, of course, colored also. So let me just return to show you this scheme again. These are the species, these cyclic species are the ones which are most susceptible to oxidation, and they are pretty well totally converted to the fully oxidized state of carbonate. There are, however, other species on the surface representing something like half of the carbon monoxide which are not oxidized at 30 degrees Celsius, and they are these species which have the ketenic character. There are then ultimately the monomeric CO species which form the carbonite, these species which are actually displaced into the gas phase as a result of the adsorption or contact with oxygen. So I can now summarize this, and what we have is a kind of oxidation hierarchy, as I called it. Here is the oxidation hierarchy then. The colored complexes typified, for instance, by the 6-membered ring, which is rhodizonate, or one can also, of course, consider other cycles like the 5-membered ring, which is croconate, or 4-membered ring, which is squarate. But if we oxidize those completely, we would have only carbonate as our product. Now, we don't have quite the full heat of oxidation as you saw. So we have a less complete oxidation than this one. We have something which is similar to this stoichiometry, where we produce, of course, much carbonate, but also there are some species which are stable to further oxidation. Now, these could be some of the less polymerized species, like the ketenic species, and I've indicated that by C3O4 2-, or they might be oxidation products such as oxalate. Notice, however, the important point that you need oxide ions in order to effect the anchoring of the carbonate to provide some of the driving force for the reaction. Now think of one of these cyclic species on what is very probably a step on the magnesium oxide structure, a place of low coordination. You need a lot of oxide ions in that neighborhood in order to accommodate total oxidation. Gradually, they will become used up. And my picture is that you get less complete oxidation, even ultimately with displacement of CO, because you exhaust the immediately neighboring oxide ions of the surface. So that ultimately what you see is some formation of carbonate which readily decomposes. So the very susceptible species are those big cyclic ones, and then these ketonic linear complexes are inert to oxidation. The absorption band at the higher energies is due to species of this kind, and they are not affected to anything like the same extent by this oxygen titration. And then the final point, the one I've made already, is that there is some displacement of CO, and I believe that that displacement of CO is coming by the decomposition of the carbonate. So that, in a sense, the oxygen titration reverses the process of the CO complex formation. You attack at the bottom end the very susceptible cyclic species. You attack less effectively the ketonic species, but you do have some depolymerization as a result of this interaction with oxygen. And that then accounts for the heat, and it also accounts for the magnitude of the uptake. So that is my picture of the reaction. Thank you.
Frankly, the heat of absorption of water on MgO is rather high. The heat of absorption of water on MgO is rather high. And in my experiments with MgO, I find it's almost impossible to prevent water absorption on dehydroxylated temperature. So when you try to do oxygen titration or CO absorption, isn't there a strong possibility that there is rehydroxylation of the MgO surface? And I have a second point, which is that when you do this dehydroxylation at such a high temperature, is it likely that you may form oxygen vacancies? And then the rapid oxygen uptake with very high heat may just be the titration of oxygen vacancies.
Well, we do, of course, do a blank experiment where we attempt to measure oxygen on the clean surface. There is negligible adsorption of oxygen. You cannot measure the uptake in terms of normal measurements, say with a pressure sensor, but the calorimeter is sufficiently sensitive to show a very tiny exothermic effect. But the amount of oxygen which is adsorbed on this 800 degrees C outgas material is negligible. So there is no question that you have generated vacancies. You wouldn't expect to in magnesium oxide, which after all is a highly refractory oxide. If you pre-solve water to a microscopic amount, you kill off the ability to form these complexes at all. So there is not, I think, any question that we are hampered here by some water impurity. That is something you've got to be very careful about. You've got to outgas very thoroughly and be able to preserve your vacuum conditions as well. Otherwise, you can't form these complexes in the first place.
One of the first ASR experiments that we carried out was on carbon monoxide and started on magnesium oxide. And we found that there were two equivalent carbons present in this paramagnetic species when we introduced C13. And it's always been a mystery to me how these C5s and C6 species could ever give such a spectrum which indicated two equivalent carbons. But I now think I understand if these, as we were saying, were really these ketonic type species rather than the C5 and C6 cyclic compounds, we could have well observed the ESR spectrum of those species.
Yes.
Unfortunately, I cannot remember back some 30 years or so what the effect of oxygen was, but I think one can now go back and distinguish the reactivity of the two types by looking at the effect of oxygen.
Yes.
One short question.
Yes, for one, in this rhodizonate and protonate and sporate species we have been observing, we know they are quite stable compounds. Now, they are very easily oxidized on the surface of MgO, so I think there is really some step of the reaction there. What do you feel about it? The real structure of these rhodizonates onto the surface?
It's very hard to explain the low energy of the absorption band, which, as you noticed, was in the region of 20,000 reciprocal centimeters, unless you've got something which is highly resonant stabilized. And this is one of the main reasons why one thinks of these cyclic complexes as being the explanation of the absorption band. And I may say that the position of the maximum is very close to the position of the maximum for the absorption of the rhodizonate ion, which you can prepare in homogeneous solution chemistry. So there is a close analogy with solution chemistry in respect to the formation of a band in that particular region. It is possible, though, that they might be conjugated linear CO species. But I think that the associated formation of the CO3 2-, which you must have if you form the cycle, is another reason why there's good reason to think that it's a cyclic species.
The last time?
Magnesium oxide luminescence when excited by UV around 250, 280. I guess the luminescence is around 400. You try to absorb carbon monoxide and to see the effect on the band of the intensity of the emission from MgO.
No, but Beluccia has done this, of course.
It is completely quenched. Luminescence is completely quenched with CO.
Is it related to, because there is the red layer model presented by Ellis, which is once we are donating the electron to the surface, we should increase the intensity, and once we are taking the electron from the surface, we decrease the intensity. How the rhodizonics are now two electrons negatively, so I would expect that they are increasing. I don't know.
Okay, I think that can follow the discussion together just after.